Okay, so finishing off read barriers and write barriers. So let's say we have two threads, right? And one thread is doing some computation. And there are two shared variables. Input detected. This is looking good, right? Okay, so two threads, they're sharing two variables, out and down. Okay, so two globals. So thread one, somehow out starts out as 5, right? It just has an initial value. And then eventually thread one sets out to 3 and then sets done to 1. You know, kind of is creating some output and then saying, okay, I'm done, that output's ready. In thread 2, we've just got some code that says if we're done. You can imagine it could be like a while done, sit there, do nothing. But if done, print out. And the question is, what prints? What are the possibilities of what prints? And what do we think we want it to print?
I want it to print 3.
You want it to print 3. You know what? Who wants it to print 3? Yeah, that seems like a good one. So 3. And we can see how that could happen, right? We get through, we get down to done equals 1, this finishes, we go ahead and say it's done, done is 1, out is 3, away we go. What are some other possibilities of what print stuff? Nothing. And that's actually reasonable too. I'm okay with nothing. But if it prints, I want to print 3. What I don't want is what? 5. Or even anything else, which would be even worse. So we don't want this. How could we get 5? Not compiler. It's not the compiler that's doing this necessarily. Likely, it's not the compiler. It's actually the processor that would be reordering your writes. So, but if these are reordered, then we could very well get 5, right? So how do we prevent that reordering? Yes, the write barrier, you said. So where do we want this write barrier? Exactly, in between the other two. Because so basically what that says is, so we add a write barrier here. And this write barrier says, basically this one, nothing from here down can be interleaved before this barrier. You can interleave all you want within the barrier, or after the barrier. You can interleave all you want before the barrier. But between two, you can't cross a barrier. Okay? So therefore, we know the out equals 3 is given. So therefore, we're guaranteed it's going to print 3, right? No. Because along with this reordering of writes, we've got also a reordering of reads. And so we're reading done, we're reading out speculatively, and because, right, we only really want to read out if done is true, but processors will read into branches to try and make sure it's not stalling, right? So we don't want to have the effect in our architecture of we read done, and then we say, okay, if go to here, and now we're going to sit and go and read out again. So it'll issue them both, and they may be reordered. So therefore, we may have read out before we read done. If we read out before we read done, we can be reading an old value of out and the new value of done. So how do we prevent that? Same idea. We need to add a read barrier, basically. So. And this is, so done is read
before out. And the right barrier is, so out is written before done. Okay? So many of the lovely things that make programming in a threaded environment hard in the face of mutable data. If you have immutable data, it's quite easy. But with mutable data, it's hard. Questions on that? All right, let me just give you a brief overview also of slab allocation. So for slab allocation, the idea is, right, in normal allocation of memory, in malloc, let's say, you've got to allocate all sorts of different size objects, right? And you've just got, let's look at normal malloc, let's say. You've got a small object, you've got a big object, you've got a tiny object, you've got other objects here, and there are different shapes and types. Okay? In slab allocation, we have all one type. So we have basically an array of same type. Okay? And if you got to allocate some other object, you have a different slab for that. What's an advantage you could think of having these same object of the same size and the same type? No fragmentation. No which kind of fragmentation? Yes, I agree. It is either internal or external fragmentation. So internal fragmentation is the fragmentation of overallocation. That is, you're given more memory than you actually need to use. External fragmentation is outside of those objects, the fragmentation. And so this would be a form of external fragmentation. Like if we go ahead and free, I don't know, this guy and this guy, then we've got external fragmentation because those two are not adjacent. We can't satisfy that. Okay, so it helps with external fragmentation. And the idea of this really is just the following. If they're the same type, then if you free one of these and reuse it later, it's still of the same type, same fields of the same type. Whereas, if you're up in the malloc case and you free an object and then you reuse it later, it could be for something very different. Why the heck do we care about this? Because if we free it, we don't need it anymore, right? But in this RCU case, remember we were talking about this concept of waiting to free things? In the slab allocation, there's a slightly different idea, which is it's really type-safe memory, which uses slab allocation. So type-safe memory basically just says when you reallocate memory, you're getting an object that was already of that type. And so if you see any old values, they were of that type. And so what you can basically do then is free memory while not waiting for the users of it to finish. So if you've got someone that's iterating through a linked list, you can just free out that linked list entry right away. How the heck can that work? Well, because that object there, we're not going to go and change it to something completely different. In fact, we could really just make a mark here that just says that, for instance, it's been freed. That's one possibility. Okay? And so the reader has to be a little smarter. The reader has to kind of look and see, oh, this thing is actually gone, and I can't use it anymore. Okay, and there are varieties of ways to do this, including a bit, including some sort of generation number, so you know data structure as a whole has this generation, and anytime you make any changes to it, you increment that generation, and you can kind of keep a generation number in this item. But that's just a kind of a very brief introduction to this idea of type-safe memory. It's really that when you reallocate, you're reallocating from the same block of things, and that's the same type. Yeah.
How is this an improvement on it not being the same type? Like, it's still the case that you just can't use it after it's been freed. Why does it matter that it has data that was like similar?
Because you can do things like say, in objects of this type, we have a bit saying whether it's
Okay, so
free or
you
not.
have the bit there.
Yeah, it's actually defined as part of the object.
Okay.
So yeah, we can share some data from free objects or old objects and new objects, where we couldn't if we were just using it as random memory. All right. Boy, that's old. That feels really old. So one more thing is about the final. So the final, which is this bad news? I haven't yet put it on the website, but I will have it as a link from the schedule like I did for the midterm. So the final is going to be take-home final. I'll pass it out in class, the last day of class. Seniors have till, I think it's 7 p.m. on Friday, a week later, right? So basically, you have Thursday and Friday are basically your final days, right? So it's the end of Friday. And then the rest of you have until whatever the normally scheduled time for this class was. I think it's Thursday at 5 the following week. So you can finish it whenever you want. Just turn it in by those times.
How long will it be?
3 hours. And it will not be open note. So 1 page of notes. Yes.
Wait, is it cumulative? Or
It is cumulative, heavily weighted towards post-midterm.
Okay.
And that's all discussed on this page that I will publish shortly.
Is the 1 page double-sided?
So here's the technicalities of that. It is double-sided. It is 8.5 by 11. So there's no poster-sized paper. And it is either handwritten or what I said is typed. You don't have to use typewriter, right? Use a printer. However, no additional magnification methods like a magnifying glass, other than your okay regular pair of glasses. And my son, when he was in high school, he learned 0 Spanish, okay, 0, because it was open note. And so he would print out this stuff at like 3-point type and take a magnifying glass. And all right, virtualization, unless there are any other questions. Oh, I do need a volunteer for Wednesday for course evaluations. Oh, they said someone responsible. Okay, it actually says responsible in bold, a responsible student. So we will designate you as responsible. Thank you. Okay, so virtual machines, virtualization. So a virtual machine is a simulation of a computer, right, running on some other computer. Give me an example. Okay, so VMware allows you to run what kind of computers?
Well, whatever operating system you install.
No, that's an operating system. What kind of computer? What kind of hardware? x86. On top of? x86, right? So it's x86, so it's self-virtualized, right? There were also emulators, for instance, for the Mac before that was x86, right? So that was x86 on, in that case, PowerPC. Has anyone ever played, is it MAME? The multi-arcade game emulator, you want to play Space Invaders or Pong? Well, maybe not Pong. Space Invaders or Pac-Man or anything like that on your computer? No one has done this? So basically it's a whatever Atari hardware emulator on x86 or Mac and so on. Goals for a virtual machine is that it be accurate, right? That it correctly emulates all the hardware, basically, how it works. You get the same results. It's isolated. That is, it doesn't interfere with any other software that's running. For instance, you might have 2 virtual machines, and they should be touching each other or interacting. other than possibly, as any machines could, via network, possibly. Okay.
So to clarify, is QEMU a virtual machine because it simulates hardware, or yes?
So yes, I don't know, and I'd have to look at what the techniques it's
Yeah.
using. So one of the things you also need is fast. Okay, and so fast. So if you just interpret an architecture, that is, write a piece of code that says, I'm going to read this instruction screen. I'm going to read an instruction. I'm going to figure out what it's supposed to do, and then I'm going to simulate that. Right? I have a big array that represents memory, and I have some data structure that represents registers, and I'll just go ahead and do that. The problem with that, can you make that accurate? Yes. Can you make it isolated? Can you make it fast? No, unless you're doing like main, where it is a machine from 30 years ago, and we're fast enough that we can run it, full speed. So you can get a Commodore 64 emulator probably, and it will run fast. But fast is especially hard if you're trying to have a virtual machine on top of the same machine. So x86 on x86. You can't afford to do that emulation, right? Because it may cost you, I don't know, order of magnitude performance. So fast is important. Why do we want to do this? You might want to run Windows software on your Linux box, or vice versa. You might want to have, a big machine with lots of core and lots of memory, and break it up into running separate things. So that was common back in the days of IBM. I guess IBM still exists. Back in the days of big IBM mainframes. If you're doing kernel development, oh my gosh, this is helpful. Trust me, you would be much unhappier if you were having to work on bare metal. Okay? So if we said, here is a machine, go ahead and create a boot disk every time you're going to test this, and boot it up and run, right? Not fun. Fault isolation. The theory here is fine. You break my operating system that's running in my virtual machine, but good luck actually now getting into my real operating system on which this is running. Packaging applications, right? You've got a particular piece of software that only runs on version XYZ of a particular operating system, and so you can package that together. Or you can also package together and hand someone something that can run, right? And resource utilization, processes can provide this too, but it can be handy to do this with operating systems. So I don't know why we have a blank page. That was a mistake. How accurate do you have to be? Really, really accurate. Even a bug-for-bug compatibility. So if you have bugs in your architecture, bugs in your hardware, you need to faithfully reproduce those. Or even if not bugs, let's say undefined behavior. Okay. 68,000 had a bunch of unimplemented instructions. Okay? Actually, a better example, back in the 6502 days, so back in the Apple II, which you all don't remember. But there were several undefined instructions, yet they behaved in a certain way, right? Because of just how the hardware is laid out. And so some software would rely on that. And so if you wanted to run that software, you would need to emulate that behavior. You have to maintain this isolation. And this is a key one. You can't, if the guest, okay, so the guest is the thing that's running in the virtual machine. If the guest can tell they're running in a virtual machine, something's wrong. Okay. Now, there may be timing differences. That's understandable, although we don't want a factor of 10 slower. Right? There may be some timing differences, and there may be some resource differences. Let's say the real machine I'm running on has 8 gigabytes of memory. The virtual machine I'm given may only have 4 gigabytes of memory. Or there may be 3 Ethernet cards on the real device, and I may only see 1. Something like that. That's fine. So the kind of resources differences, that makes sense. Timing differences makes sense, although we still want fast. So some virtual machines, for speed reasons, right? If you are, let's say, a virtual machine provider, like Microsoft has a VM, don't they? Okay, so Microsoft has a VM, and you also provide the software that you're trying to run on. You can actually improve things by making the software know it's running on a virtual machine and do some things slightly different. I'll give you an example. You've got a virtual machine that wants to go allocate a page, okay, a free page. And so it goes and allocates a page and zeroes it out. How does it allocate a page? I mean, eventually it's going down to the base operating system, let's say, that itself will allocate a page. That also will zero it out because it wants to make sure that no data from any other process that this virtual machine can see. So there'll be two levels of zeroing out. The virtual machine monitor, the VMM, is going to be doing that for isolation from any other programs. And then the guest operating system will also be zeroing it out, not realizing it's already been zeroed. Now you say, why don't you just check if it's zeroed before you zero? You're not going to say that, are you? No, because that, yeah, it's just as fast to just zero it out. But yes.
Sorry, when you refer to a virtual machine, just to be specific, are you referring to the guest operating system?
Yeah, let's go ahead and use, so here's what I'm going to look at. We have our hardware. We have our VMM, Virtual Machine Monitor. Okay, sometimes called a hypervisor. Okay, so the VMM is the thing that's responsible for this virtualization. And it then provides the illusion of virtual hardware. So it's going to provide virtual hardware for one guest OS and also virtual hardware for another guest OS. And then on top of that OS, the OS is unaware that it's running this way. And these applications are, of course, unaware that they're running not on the operating system they see them on, but on something. Now, in some cases, this VMM is very small. As an example, in the IBM case, there was no real other processes running back for IBM 360. They just had a very small VMM whose only job was to create virtual hardware for other OSs. It was not really its own OS, and you never programmed it. Commonly, though, these days, this is a real OS. This is Linux with a virtual machine monitor running, or Windows with a virtual machine monitor running. My understanding is Windows 7, 8, 9, 10, something like that, has a virtual machine in which it runs XP. Okay. There is a virus out there, so that will take over your boot sequence and install a virtual machine in which it then runs the real OS, so that the real OS can't tell that it's been on. Okay? So, how do we pronounce that? Oh, sorry. That O is pronounced as an O. So that is a very simple virtual machine monitor because it's not providing any other features besides doing whatever its nefarious things are and then providing this VMM to, let's say, Windows or Linux. Does that help with the naming? Okay, so started in the 1960s. In the 1970s, there were some specialized hardware to do this virtualization. It kind of was not that big in the 80s and 90s because the architectures that we're going to talk about this, the hardware didn't provide any support for virtualization. And so it was considered very difficult until really VMware came up with a fast way to deal with the x86. And so that's been popular since the 1990s. And then in 2000s, and we'll talk some about this today, AMD and Intel both specialized their CPUs. So they both did their own thing, okay, which provides similar sorts of services, but different implementations. So anyone who's writing a VMM has to have different code for Intel and for AMD. Does anyone know why AMD has x86 architecture? So IBM, developing the PC, right back in the early 80s, decided on, right, they wanted to use off-the-shelf components, including the 8086. At that time, I believe I have this right, Intel was the only provider. And IBM said, well, we don't want to be stuck sole sourcing the CPU. What if you guys go under or something else? And so Intel was forced to license it to AMD. And so Intel and AMD then, or AMD then had a license for x86. And Intel regretted it later, but I guess at the time it was good. So this is our pre-example. OS running directly on hardware with our apps. And this is our post picture. So the VMM is providing an abstraction to the software that runs on top of it. Commonly, the abstraction OSs provide is processes. This is a different abstraction. Okay? So this abstraction is hardware. So a normal OS provides processes. A VMM provides a hardware abstraction, because it's not entirely real. So a process, you have non-privileges, right? If you're a user process, you can use non-privileged registers, like you're not allowed to deal with CR3, right, page table, and non-privileged instructions. In the hardware abstraction, you're allowed to use all registers and all instructions. Even privileged ones? Can I deal with a page table register? Yeah. But here, actually, can I switch from privilege level 3 to privilege level 0? No, not unless you do a trial. But other than that, no, you're just not allowed to do that. Can I here switch from 3 to 0? Yes, because I'm having to write an OS. I think it looks to me like I have everything I could possibly do with hardware, including all the privileged instructions I can. Process, we have virtual memory. Here we have virtual memory and an MMU. Right? We have virtual addresses. We get to decide what physical addresses they go to. We get to deal with traps, interrupts, and write trap handlers, and enable and disable interrupts, and so on. Here all we get are signals. File systems and sockets, no, we're way lower than that, right? We're I/O devices. And DMA to those I/O devices. Because it has to look the same. Now, the I/O device that's there might be emulated. There might not really be an I/O device there. Just like for all of you guys who are doing Lab 6, there's no actual E1000 necessarily on Knuth, right, where you're running. But it sure looks like it to your code. All right, so how can a CPU be virtualized? That is, be able to run it on top of itself. Classic virtualization says you need 3 things. So you need fidelity. That is, you need to make sure that it runs identically. You need performance. This is what they require for performance, although it turns out this wasn't strictly necessary for performance, as VMware showed. Well, I even back up that. Yes, this is VM, so VMware still does this. It's just in a way that they had not thought of. So performance, run an overwhelming majority of guest instructions executed by the hardware without the intervention of the VMM. That is, you're just running hardware instructions and they're running. So that you've got mostly full performance. And then sometimes you may have to dump into software to do some things. But as long as that sometimes isn't very often, then you're going to get good performance. And then the safety, you're just not
handing out hardware unprotected
to the guest. The simulation, I talked about this, right? It's basically performance is the problem. So unless you're trying to emulate something from the past or something very small, you don't want to do that. So here's our idea. We execute guest instructions in the real CPU whenever possible. That's the sweet thing. That works great for most instructions. If you're trying to add EAX, EBX, just do it. That's great. The problem is privileged instructions, right? Instructions that for instance, try and modify the page table register. You can't just directly execute those on the real hardware because you don't want this guest operating system to change the real page table. Because then, if they can change the page table, they can adjust what's in the page table, and they can go look at any other piece of physical memory. Right? We don't want that. Does that make sense? So, why don't we do this then? Why don't we run our kernel at CPL3? So we'll run it so it doesn't actually have access to privileged instructions. Okay? Ordinary instructions, like adding two registers, will work fine. Simple things, reading from memory, writing from memory, will work fine. But as soon as you try and use a privileged instruction, you'll get a protection fault. Because you're trying to write the page table register, and it's not allowed in user mode. And so you'll get a trap to the VMM, right? And the VMM can then look and say what was trying to be done. Okay. Were they trying to write the page table register while they were in simulated CPL0 mode? So we'll have to keep some idea of what mode they think they're in. Does the guest OS think it's in CPL0 or CPL3? And then if it's in CPL3, then it would pass this trap on to the guest OS. So we've got an app running on our guest OS, and then this is in our VM. Here, this is CPL, I'm going to call this pseudo CPL3, and this is pseudo CPL0, and this is real CPL1, 3. So if we're in pseudo CPL3 and we try to read or write CR3, right, which is the page table register, we'll get what? We'll get a fault into here. Okay? So we get a fault protection. We can go look, see what it is. And now what do? We say, what pseudo mode is this in? Okay? So we're going to have some idea of this virtual machine, of what mode it thinks it's in. Yes?
When you get a trap, the general connection fault, don't you get it in your host OS?
Nope. Here's why. Well, we will eventually, but the hardware is not going to do that. The hardware is just going to go to the trap table. And the trap table is the trap table the VMM installed. Because the VMM doesn't want this guy to install a trap table. Because then it's taken over the entire OS, basically, right? So it's going to go here. And this guy's going to go and say, oh, we were in user mode. And so therefore, we need to forward the trap to here. What does forwarding the trap mean? Go look up this guy's pseudo trap table, right, that it thinks it's set. and call the appropriate trap. And this guy will then get it. And what it's going to see? It's going to see general protection fault from here, and it's going to say, bad app, I'm killing you, or something. Whatever it chooses to do with that information.
So you're saying that VMM can install this trap table onto the host OS?
The VMM is an operating system, and it has installed a trap table. It has installed the real trap table, the one the hardware is going to look at.
So the VMM is different than the original OS. I mean, it's the same as the host OS.
It's the same as the host OS.
So
Yeah.
Linux is a VMM.
Linux,
If we're running like,
you can run VMM software on it, and so yes, we can look at Linux as being the VMM. Sure.
So does that mean if you want to install like VMware on Linux, you have to like install a kernel module or something like that?
You would have to, yes, because you have to have CPL0. So it's not just a regular application that's running. This is running in CPL3, sorry, CPL0. Okay? Real CPL0. So this is the real operating system.
so whenever you install like VMware on an operating system, it installs its own thing into your kernel.
It's going to have to.
Okay.
Let me back up a second. No, not software VMware. So we'll just, that's a different story that we will get to. Go ahead.
So just to be clear, so say I'm an app like the one
Yeah.
here, and if I hit a page fault or some kind of a fault, I will go into the VMM, and then it's the VMM job to kind of branch out whether I go to the guest OS to do something, or maybe something related to the hardware if it was the case that the pseudo CPL was the one it was doing, trying to do something with the hardware.
Yes, I'll give you an example. So if we do here, this is going to end up as a fault in here. If we now do write CR3 here, will we get a fault? Will the hardware get a fault? The hardware will get a fault because we're still in CPL3. So we go in here. It looks and it says, well, we're in pseudo CPL 0, so this should be allowed. So I'm going to now have some code that allows sort of a pseudo CR3. Because I'm not going to allow them to change CR3. They can't just go change the page table. But I'm going to make them, allow them to set up their pseudo CR3 to point to this page table. Okay, so I'm going to be simulating their page table. We'll talk about page tables later. We should have maybe looked at a simpler instruction. Yes. Let's say enable interrupts. That would be a good one. So if you enable interrupts, all this is really going to do is just control a flag that says are interrupts enabled or not enabled.
So if you manage to get a trap forwarded to the guest OS, it can modify the hardware in the VMM, but it can never go and actually modify the
It never actually gets to go and modify the real hardware. No.
no matter what.
Yeah, it's never going to be able to go and modify CR3. It's never going to be, it can go and modify, all sorts of other regular old registers, but not something like that. It can't really change the CPL. It's just as far as it's concerned, it thinks it's changed it, and everything acts as if it's changed it, but the real hardware's not doing it. So this is called trap and emulate. Right? The basic idea is anything that's not privileged, anything so this is anything that requires CPL 0 or so you could tell what mode you're in. Okay, all of those should trap. If they trap, it's fairly easy to write a VMM. Okay, what do I mean by tell what mode you're in? Well, just happened. let's get to the moment. Let's just first look at the simple cases. So clear interrupts, set interrupts, right? You want to enable, disable interrupts. Not allowed in CPL3, right? So they'll trap to here, and then they'll just be a status block for this guy. And it will include, what is CR3? It's going to include interrupts, on, off. It's going to include a lot of state information, okay? That normally is kept in hardware. But this is going to be instead in software for this particular guy. So if this guy says I want to turn interrupts on, it's going to just go change this bit. If they say I want interrupts off, it's going to go change this bit. Is it going to actually turn interrupts off? No, it's an operating system. We can't just turn interrupts off, right? That'll break everything. Yes.
Does the VMM have any access to that information?
The VMM is in complete charge of this information.
Oh, so that
It controls
controls
this.
Okay, it controls it. So it still has to go through the VMM to do all of that.
Any updates, reads or writes to this, are done by the VMM. Okay. So some of what's happening is just changing state in this control block. So we have virtual copies of E-flags, which is where we keep track of whether interrupts are on or off, right? That's a bit in E-flags. So VMM is in charge of the hardware, E-flags, and it maintains this copy for the guest. So let's say an interrupt comes in. Let's say there's a serial port, okay, that the VMM has set up for the guest. So it has specified that the guest has exclusive access to this serial port, just to make life easy. So there's no other VMMs that are installing. So if a serial port interrupt comes in, where would it go? In hardware, it'd come to here. As far as this guy's concerned, he should forward it onto here. Always? No. Only if this guy has enabled interrupts. If this guy hasn't enabled interrupts, it doesn't want interrupts. So the VMM will get the interrupt from the serial device. It will look up and it will say, who did I assign this to? Oh, I assigned it to this particular VM. Here's the control block. Let me look. Does it want interrupts or not? If yes, send it on. If not, drop it on the floor. Does that make sense?
The status block for each VM, like how closely does that mirror, like, I guess, that same information in the hardware? Like, because the CR3 and E-flags, that all exists in the hardware, and you have to keep track of it for each VM, but are there things that, like, it doesn't have as options? Like, the VM doesn't have as options to modify, like an OS on the hardware.
If there's something that an OS here can't modify, that it could in real hardware, then we fail the fidelity test. So we have to completely match. That's what happens. What about virtual memory? So let's look at what happens here. The VM thinks it has this dedicated physical memory. All right? Contiguous physical memory. Does it really have contiguous physical memory? No, because this VMM may have patched together, you know, pages here and here and here and here, right? So we've got this contiguous guest physical memory. Okay, and it's guest physical memory because as far as the guest is concerned, it's physical memory. And so it's got, you know, I don't know, 0 to 2 gig. Does the hardware have to provide this as 2 gigabytes of contiguous memory? Why not? How can it get away without providing? Yes.
Wait, isn't the contiguous guest physical memory that this guest was perceived actually virtual memory? Like
Oh, that's why, because it's really virtual memory. Yes, it's really virtual memory. So this is really virtual memory, and so we have the real physical memory, the host physical memory. It might be larger, right? This might go from 0 to 4 gig. And we're going to have pages, right? So this is one page, and here might be another page. And here might go nowhere. We might have no memory allocated for this page, right? Yet, if the guest OS tries to use it, it should act like it's there. But we know how to play that game with virtual memory. Okay? So we know how to play the virtual memory game to do this. And the MMU is going to be responsible for translating from these guest physical memory code. The problem is, yes?
You might touch on this now. I was going to ask about guest virtual memory.
The problem is guests have virtual memory. So guest thinks they have a MMU, right? The guest has an MMU. How do they control the MMU? How do they program the MMU to do what they want? How do you, in JAWS, control the MMU? The CR3 register, or more generally the page table, page directory, page table, right? So you set up a page directory and page table you want, you set the CR3 to point to it, you also have some control over invalidating, right, pages in the TLB. All that should work from your point of view. So there's you guessed VM, virtual addresses, and they map, let's say, here to here, and here to here, and so on, right? Not contiguous. Just make it clear that's not contiguous by making that one go to there, let's say. This mapping is based on the pseudo CR3, right? The guest's idea of CR3 and its page table that it set up. That's how it controlled this.
Wait, sorry, so isn't the MMU like kind of done in hardware? Like,
MMU is done in hardware. We have no idea how to implement this yet. We're talking about how we might implement it.
oh,
There's only one MMU. How the hell does this work? Right? So how is it we can get a virtual address here, and if we say, you know, this contains global variables, and we say foo equals 3, how is it that foo, which is in this virtual frame, in this guest physical frame, in this real physical frame, so foo is over here, how do we get from here to here? So from here to here to here. And the answer is, we as the VMM need to make sure that a virtual address from here maps all the way to here. Can we do this? Yes.
So you're saying that the guest OS would have the mapping between the
Guest OS does this.
yeah, and then the VMM would have the mapping between the guest virtual address and the real, like.
This is what we start out with, that the VMM has this mapping. It knows what pages it is mapped for the guest OS. But the VMM also has access to this page table, right? Because it can look at this CR3. It points to some place in memory here. You know, it has a way to do that, right? It points to the CR3 points to here. No, because remember CR3 is a physical address. So it points to here. So the VMM can follow C3, go into, let's say, here, find the page table, I'm sorry, yes, go into here, and then go into here, and actually, sorry, go into here and read what the page table is. So it can actually read the contents of the page table. So it can read the guest OS's page table. It knows this mapping, and now it can then manipulate the MMU. So that while this virtual machine is running, we'll have the right mappings. So here's what happens, right? So host virtual address, host physical address,
Right? This is the host page table. This is the VMM. The guest has this virtual address that goes across to a physical address, and then the VMM mapping goes across to a physical address. And this shadow page table is basically the page table that the VMM is going to set up. It goes directly from guest virtual address to host physical address.
So that's the shadow page table is a separate thing from that basically spans from the leftmost read memory to the rightmost.
So this is controlled by the guest page table, right?
Yeah.
So this is the guest page table.
So the shadow page table spans from the guest virtual memory all the way to host physical.
Yes. And it can do that because it knows this mapping.
Yeah.
And it knows what this mapping is. And then it just sets up the MMU to combine those. Okay? Yes. This is without hardware support. It would be handier if the hardware kind of had two MMUs. And so we will cause that to happen in a moment.
So instead of having the host page table be stored in the CR3 register, the shadow page table be stored in the CR3 register so that the guest virtual addresses are being.
The real CR3, the hardware CR3, is going to point to this page table. Yep. So this is the real page table that's being used, which is an amalgamation of the guest's page table along with the OS's page table, which is keeping track of what we have allocated to the guest and what physical addresses do.
So do we put the shadow page table in the real MMU?
Yep, this is in the real image. Because
Otherwise it's just.
we're going to execute an instruction that says read from this virtual address, or write this virtual address, and we want it to go to the right physical address. We just have the one MMU until we make another one to do that.
There's a VMM map that is stored you said OS earlier?
In the VMM.
In the VMM.
The VMM map is controlled by the VMM.
So the shadow page table is just basically like fast access of those virtual addresses?
No, it's because it's because we want to be able to run this instruction. Move. I'll tell you what I mean by this, is move whatever is at this global variable, right, at this address into here. Okay? So read from this address, move it into here. This is what kind of address? Guest virtual address. I want to be able to run this at full speed. That is, I want the hardware to do this and not me not get involved. And so the only way to do that is to make sure that the hardware has this mapping from guest virtual address to physical address. Otherwise, I'm going to have to be looking at every single time we deal with reading or writing to addresses and doing this translation. That's going to be just awful.
So do you mark in the shadow page table the guest virtual addresses that have the guest page tables as read-only so that they trap when the guest tries to write to them, and then...
So yeah, how do we keep our shadow page table up to date? And so if the OS changes CR3, it's fine. We know they changed CR3, we can go look at that. If they update the page table, some updates cause the TLB to be flushed, right? Some updates, the OS had better do a TLB flush. But on some, they don't necessarily do a TLB flush. Like if you delete a mapping, I think. So commonly, you'll do a TLB flush, and they could be looking for that TLB flush. And then, once you get a TLB flush or they change the CR3, then you can go ahead and reread those page tables. For the cases where you don't have to do a TLB flush, then the other thing to do is mark the page table itself in the real MMU as read-only. And if the guest OS tries to write to it, you'll get trapped. You can allow it, but then know that you have to update. So reread that page, because the page table changed. Questions? Yes.
Can I ask about that? So
Yes.
I noticed that you did like destination source.
Yeah, Intel, AT&T, sorry. And the problem is, go ahead.
Which one should we be like using for stuff? The other way, right?
What we have been using on is the other way, right? I believe that we do source test, right?
Yeah.
Well, hell, this works fine too. All right? We're just writing from this register into here. Yeah, you just, the only difference is whether it's a read or a write. Such a slight difference.
Okay, so the guest wants guest physical page at OX1 with a lot of zeros. Right? So it's saying there's a physical page at what I think is physical OX100. The map maps it to 2000. And we have to have a mapping right, in the MMU may have a mapping from 35600 to 200000 if the guest page table goes from 35600 to 100, and then every mapping goes here. So the shadow page table is a composition of the guest OS's page table and the VMM's mapping. And why can't we just modify the guest page table? Right? They had a page table they carefully set up here. Just go change the physical addresses and set that to the real CR3. Could the guest OS notice that you've done that? Yes. And if they can notice you've done something, that's no good, right? They write a physical address here in the page table, and then they come back 2 seconds later and it's changed. Not okay. So that's why we have to have a shadow. Now here's a big problem though. Trap and emulate, you can't do it on x86. At least you couldn't until they started adding hardware virtualization techniques. 2 reasons. Some instructions behave differently. If you're in CPL3 and they don't trap. So you can tell the difference. The CPL3 and CPL0 work differently, and the CPL3 one doesn't trap. So you can see if we're trying to run our guest OS at CPL3, we've got a problem, because they can use one of these instructions and tell the difference. Second, some registers just leak state that tell you what mode you're in. And they don't trap either. So that violates the fidelity because you can tell. It's as if you guys were able to tell that you're in a simulation, right? Have you all heard the argument as to why, in fact, it's likely we're in a simulation? Because simulations will be possible. And when simulations are possible, if we assume they don't take too many resources, then there will be lots and lots and lots of simulations in the future. So given the number of simulations there are, it's more likely than not that you're in one of those, that you're actually in real life. Okay? Anyway, if it's the fidelity, right, is perfect, except maybe we're running slower than we should be. I don't know. But anyway, fidelity is perfect, you can't tell the difference. So example of different behavior. The CS register, the code section register, has a CPL and it's lower bits. See the CPL. That's the problem. When you pop and push flags, the E flag, so they thought to be smart and said if you're pushing and popping E flags in CPL3, we will not tell you about the interrupt state. We don't want you to know about that because that's reserved for the operating system. Well, it would have been better to say, oh, let's just let the operating system decide what to tell you by trapping the operating system. But they didn't. You just get masked down. So you can tell the difference. And if you do an IRET, you remember that one, then it operates differently if you're returning from CPL0 to CPL0 than if you go from CPL0 to CPL3. Because it actually needs to deal with the stack. So if you're doing an IRET, it assumes there's a new stack pointer and stack segment. So that's a problem. And on a trap, the same thing happens. So when you do a trap, it depends on what mode you were in. So 2 possible solutions. 1, fix the instructions that are bad. Fix when someone does let's say, a pop FL, so that when they pop the flags, it goes ahead and looks to see, are they in pseudo mode 3 or pseudo mode 0, and do the right thing appropriately. So we could theoretically search through all of the instructions to look for a pop FL and just replace it. There are actually a lot of problems with that. Okay? What we're trying to replace it with is longer, because we need to actually do some checking and do something else. But we could fix that. We could just trap to the VMM to deal with it. And we could trap to the VMM with like an interrupt 3, which is a small instruction. It's 1 byte, so I can put it anywhere. I could replace a pop FL with a trap, and maybe I need to put a couple no-ops just to fill in however big the instruction is. So that'd work. But we'll see there's other problems with that. The other solution would be have hardware virtualization. Fix the x86 architecture so that it no longer does this. And we're going to see that in a moment. So here's the biggest problem with this. We could replace bad instructions with an interrupt that'll then go to our VMM that can do the right thing. The biggest problem is, how do we find instructions? It seems simple, doesn't it? Except, what's code, what's data, right? We just don't want to replace every byte that looks like a pop FL with a trap, right? Because now you're changing your, what are you changing? You're changing your tables that you use for shooting your cruise missiles, right? And that's probably a bad thing. Maybe they shouldn't even been running on a VMM, but so that's one problem. And the other problem is, like, there's self-modifying code out there, right? Or code that gets generated on the fly, like the Java VM dynamically generates code. Or we talked about the packet filters a few weeks ago, where we're loading code into a kernel that's dynamically creating code. So we can't statically go through and figure out the instructions that are a problem. In fact, we could probably use prove that it's not possible to find them, right? Because if we could solve that, we could solve the halting problem. Anything at all interesting about a program, we can't really tell. So here's what we do instead. We're going to translate the kernel dynamically. So as the kernel is executing, we're going to be taking instructions, and we know they're instructions because they're about the program counter is pointing there. So we're about to execute them. Okay? So we scan as we execute, because the execution tells us instructions. And not only that, when we've got an instruction, we probably know what the next instruction is too, and that it's an instruction and what it is. And the next instruction, until when? When do we no longer know? When there's a jump, right? When there's a jump, we're somewhere else. And if it's a direct jump, then it's not so bad. If it's an indirect jump, it's definitely more difficult to figure out. So we'll just go and translate a small bit of instructions, just from where we are to the next branch. Or 12 instructions, a maximum of 12. Okay, so we're doing these tiny little blocks. And we're going to have this translator whose job is to translate one of these basic blocks and just find any bad instructions in it and change them appropriately. So instructions that won't work in CPL3. And these will also be instructions when we are in CPL0. So we can look for a pop FL. And we can do the appropriate thing. Now the appropriate thing isn't going to be doing a trap necessarily. Maybe we can actually make something faster than that. But to begin with, we can pick the idea of just finding any bad instruction and doing a trap. Does that concept make sense?
How do you know what the appropriate thing to do is? Is that like a pre-coded thing?
Yeah, we're going to have a big table of what to do. Pop FL instructions are going to turn to this. Push FL instructions are going to turn to this. We're going to just have a whole list of them. most instructions, and this is the key point, translate identically. Most instructions translate identically so that we'll be able to run full speed. Now we're going to translate this basic block every time we see it. Just the first time. Okay? Although I guess we'll have to have a little bit of checking to make sure that they haven't modified the instructions with self-modifying code. So when we first load the kernel, we know where we start, right? Because the hardware defines where you start executing. And so we saw in JOS it was, or in x86 it was somewhere in low memory. I don't remember where. Somewhere in low memory. That's where we'll start. So we'll go to there, get the first instruction, go from there for 12 instructions, or to the next branch, translate those. And we only bother doing this if we're in CPL0 mode. If we're in CPL3 mode, right, in pseudo CPL3 mode, then we don't bother. We'll just go ahead and let it execute because it's CPL3 code. We're in CPL3 mode. Can't tell the difference. I'm going to ignore that one for just a second, and that same address space for just a second. But just know that the VMM is running in the same address space as the guest. And I'll talk about this more, but the guest will be here in our address space. This is where the guest is. And the VMM is hiding down here. Okay? Yes?
So we're VMM running CPL3?
Yes.
How does that work if there's multiple, like, guests that the VMM is supporting?
There's multiple ones. We could have separate address spaces using, this uses segmentation, is how they do this. So VMware does this with segmentation by setting up basically all the segment registers, limit what it can see to hear. And there's one segment, which is the GS segment, that actually includes the VMM. So I'm going to just ignore that for right now, though. So we have this translation example. So what happens? We go through and we look at, so this is just the code for Prime, with some added labels in here, some meaningful labels. So we, and this is the destination and source. So this is not what we're used to as far as this. So we move, sorry, we set ESI equal to 2, we compare that to A. So A is actually in ECX. So we compare it, and if it's greater than, we jump to 5 back to here. And then we've got other stuff in it. How many basic blocks do we have? There's 4 labels. So is the answer 4? No. Here's one. Would we agree with this? This is a basic block, right? This basic block goes until where? Yeah, until the JZ. So this is a basic block. This is a basic block. This is a basic block. And that's a basic block. But we're only worrying about the first one. So we go through and we translate that first one. And I don't know how this happened, but we lost some instructions in the translator. So the translator was faulty. And we have another move, and we have a compare. It's not good there. Okay? So this is the original here. And we convert that to, it basically looks, it says this instruction, fine. This instruction, fine. This instruction, fine. There's nothing that matters as whether it's in CPL3 or CPL0 here. And this instruction is a branch. So we are now going to break that into 2 things. So we have 3 instructions, move, the other move, compare, jump greater than or equal to. We can't jump to this label, to this address. Okay? We may have changed the number of instructions here. So basically, all of the addresses may be changing. So we're going to jump to, this is called like a continuation.
You can't jump to that address because you need a CPL privilege.
No, it's not that we need the CPL privilege. It's two things. One, we don't actually want to execute the code at that address. We want to translate the code at that address before we execute it. And we can't translate it in place because of varying sizes. So we make it bigger. So we're going to have to actually turn this before we go there. First, we're going to need to translate this, whatever it is, and then we're going to go to the new place. So we're going to actually jump into the VMM.
Oh, I see.
So this is going to go into the VMM. All right? So this is going to actually
Sorry, is that the taken address?
the taken address is in the VMM, and this address is the VMM too. So this is a VMM address and a VMM address. Okay? Here's what's going to happen. Let's say we let me back up a second. We translated this. Okay? We now have this new address.
Yeah. So you can't do.
Okay, so we have a new address here. And we have a big hash table that says the old prime address goes now to the new prime address. Okay? And so for this taken address, so what happens when we do a jump is it first looks and says, have we already translated that? And in this case, we have already translated. So this is going to go to here. It's going to go to the new prime address. Yes?
Wait, sorry. Why are we jumping back to the beginning of the function?
Because we've got a for loop.
But like, shouldn't when you check, why would you jump back?
Oh,
Seems like there's a typo here.
there's a typo. All right. Let's say that we had a loop that goes back. We've seen such loops, right? This isn't one of those, but we've seen such loops. So if we go back, this is what would happen. We would look, we would say, oh, we've already translated that basic block. We'll just go directly to that basic block. The problem we have is this particular code. This should be is prime, because we've got a prime down here. Okay? So this should be is prime. And so we're not going to go back here. We're going to go into the VMM because we look and we see that the taken address is not in a hash table. Okay? And then we also convert, normally we just drop through, right? In our original code, we drop through into next I. Here, we can't just drop through. We have to actually jump there. So we're going to jump to this fall through address. And we again look and we say, okay, next I. Is next I been translated yet? No. So therefore, we're going to go into the VMM. And then in the VMM, its implementation of this is going to be translate that address. So if we take this path, it's going to go into the VMM, and it's going to say, okay, translate from next I on. If it goes through this path, the VMM handles this and says, goes to that address. And then it puts it in the hash map, and it fixes up this range. So once it's translated it, it goes back in and fixes this jump greater than to the actual translated value. so that second and subsequent times, it doesn't have to retranslate. Second and subsequent times, it's running at full speed. So it puts a temporary jump in here into the VMM so that the VMM will get control whenever we reach that. Right? We don't know as the VMM which of these branches we're going to take because we haven't executed this yet, right? We translate it and then we start it running. And so we want to make sure we get control back when it goes to either one of these. And then we get control, we translate that one, and we throw it to run again. Okay. Does that make sense? Sort of.
How like fast is the translator, and does it?
It's fast.
So does it get to a point where like it's translating in about one speed, or does it like batch things where like it could fall behind?
There's no falling behind. There's no falling behind because there's just one locus of execution, right? It's just translate a basic block and then let it run and wait until you're asked to translate another basic block, right? And when you're starting, it's like translate one and it runs and then you come back and you do another one. And you run, you come back and you do another one. And more normally this gets cached, so most of it is just running full speed. All right, we'll finish this up on Thursday.
Oh, wow. Is that like part of your 12 hours?
And I'll be in the cafe until 4.